Welcome to SciFlux. Here you get daily coverage of the latest scientific research. Every day, we bring you new research in a clear and simple format so you can stay informed without wasting time. Like the video, subscribe, and leave a comment to stay connected and help this channel grow. And if you want each new research delivered directly to you, join the SciFlux newsletter. This review highlights how 3D printing is transforming orthopedic implants by enabling fully patient-specific, biocompatible solutions. By using additive manufacturing with individualized scans, surgeons and engineers can produce implants that fit perfectly, optimize function, and improve recovery outcomes. The study emphasizes both the advantages, faster production, cost efficiency, and enhanced healing, and the challenges, including regulatory, material, and ethical constraints. It positions 3D printing as a strategic roadmap for personalized orthopedics, paving the way for future innovations in materials and design that could make custom implants increasingly precise and universally accessible. This work provides a complete step-by-step mathematical foundation for Grand Canonical Monte Carlo (GCMC) simulations, essential for designing advanced materials for hydrogen storage, carbon capture, and other clean energy applications. By explicitly deriving the underlying equations from the metropolis criterion and detailed balance to gas mixtures and real-world calculations, it makes the simulations fully transparent, reproducible, and easier to improve. This resource strengthens both education and research, enabling scientists to build accurate, reliable computational models and accelerate innovation in materials science. This study demonstrates the educational power of our mixed reality by combining physical and virtual models to teach Earth's rotation and orbit. By allowing students to interactively explore day-night cycles and seasons, the approach enhances understanding, motivation, and curiosity. Mixed reality proves to be more effective than traditional or single-mode tools, providing a hands-on, immersive learning experience that makes complex scientific concepts accessible and inspires deeper engagement in science education. This research applies advanced AI to solar activity forecasting, using deep learning models like CNNS, ResNets, LSTMS, and large frameworks such as CLIP and MASK autoencoder. By uncovering complex patterns in solar data, these methods outperform traditional forecasting, enabling more accurate predictions of flares and coronal mass ejections. The work enhances protection for satellites, astronauts, and critical infrastructure, demonstrating how AI can transform space weather prediction and risk management. This study enhances electronically assisted astronomy (EAA) by combining AI with contrast improvement techniques. Methods like linear contrast, stretching (CLAHE), gamma correction, and grayscale transformation were applied to noisy low-contrast amateur images, improving the performance of AI models such as YOLO 8N, YOLO 11N, and YOLO 12N. The approach enables more reliable detection of faint celestial objects, making the A more accessible and empowering amateur astronomers to contribute meaningful data to real scientific discoveries. Next paper. This study looks back to the universe's first few 100 million years, using observations from the James Webb Space Telescope, which is already challenging standard models of early galaxy formation by revealing galaxies that are larger and brighter than expected. To test this, researchers ran high-resolution simulations of the first galaxies, directly comparing 6 state-of-the-art simulation codes under the same physical assumptions. For massive halos, the models successfully matched James Webb Space Telescope observations of stellar mass, metallicity, and luminosity, particularly in the redshift range 10 to 12. However, at even earlier times, the simulations still fall short, underestimating galaxy properties. The work also underscores the critical impact of stellar and black hole feedback, as well as the role of dust in amplifying or suppressing observed brightness. Bottom line, current galaxy formation models can explain part of JWST's unexpected results, but the very first galaxies remain unresolved. pushing to even higher resolution simulations will be essential to close this gap and fully understand how cosmic structure began. This paper explores Gaia's rapidly evolving role in exoplanet discovery and the new forecasts reshaping expectations for the mission. Gaia is primarily known for mapping our galaxy, yet it's on track to become one of the most powerful exoplanet hunters ever launched. As exoplanet science advances and Gaia's own astrometric precision exceeds expectations, earlier predictions for its planet yield required a full reassessment. Researchers approach this with a dual methodology. A semi-analytic model established the fundamental scaling laws for astrometric detection, and extensive Monte Carlo simulations added real-world complexity, from stellar variability to Gaia's observational cadence. Together, these tools produce the most realistic forecast to date. For the 5-year DR4 release, Gaia is expected to identify around 7,500 planets, plus or minus 2,100. Over the full 10-year mission, DR5, that number jumps to about 120,000 planets, plus or minus 22,000. Importantly, Gaia won't just detect them. Approximately 1,900 planets in DR4 and 38,000 in DR5 should have masses and orbital parameters measured to better than 20% precision. Most discoveries will be super Jupiters, 3 to 13 Jupiter masses, typically orbiting G, K, and M-type stars within 500 parsecs. False positives from unresolved binaries remain a factor, but genuine planets should outnumber them at least 5 to 1, with higher contamination only in close-in orbits around M dwarfs. To prepare the community, the team has also released mock catalogues to support early analysis. This paper explores Gaia's rapidly evolving role in exoplanet discovery and the new forecasts reshaping expectations for the mission. This study explores one of the most elusive moments in stellar evolution, what a young star is like before it erupts in a powerful Fu-Ori outburst. These events, where a star suddenly accretes matter at extreme rates, are believed to be central to how sun-like stars and their planetary systems form, yet their precursors are rarely observed. Researchers focused on HBC 722, a young star that was fortuitously observed years before its well-known outburst. By combining a low-resolution optical spectrum with archival photometry, including critical U-band data, they reconstructed its pre-outburst state and disentangled stellar light from dust extinction. They found HBC 722 to be an M3.3 star, about 30 to 50% of the Sun's mass. Before erupting, it accreted material at roughly 7 times 10 to the negative 9th solar masses per year, high for its type, yet about 15,000 times weaker than during the outburst itself. Archival data also showed strong variability, with brightness changes by a factor of 5, consistent with unstable disk accretion. Unusually, the star's radius was about twice that of comparable young accretors, and dust obscuration was significantly lower prior to the outburst. By capturing this rare pre-eruption snapshot, the study provides critical constraints on the conditions that trigger Fu-Ori events. These insights refine models of stellar assembly and protoplanetary disk evolution, offering a clearer view of the processes shaping young stars just before they dramatically transform. Next paper explores the violent and chemically rich environments surrounding massive newborn stars. When giant clouds of gas and dust collapse to form a star, protostellar outflows blast material into space. While previously seen mainly as dynamic structures clearing the surroundings, new research shows these outflows are also active chemical factories, shaping the molecular content of future star systems. Astronomers focused on the massive star-forming region, IRA S16272-4837, SDC 335, using ALMA, combining data from the ALMA-ATOMS and ALMA-QUARKS surveys, Observing at 1.3 and 3 millimeters, they captured high-resolution spectral line data to map both the physical and chemical structures of a bipolar outflow. The results revealed a complex system, a high-velocity jet surrounded by a broader, slower outflow cavity, with bright knots indicating enhanced molecular activity. Across the outflow, they identified 35 molecular transitions from 22 species. Three main mechanisms drive this chemistry: direct entrainment of molecules from the natal core, shock-induced release of molecules from dust grains, and thermal desorption plus gas phase reactions caused by heating from shocks. These findings demonstrate that protostellar outflows are not just material conveyors, but dynamic chemical reactors, enriching their surroundings with molecules critical for planet formation. This work reshapes our understanding of chemical evolution in high-mass star formation, revealing that the building blocks of future planetary systems can be forged in the violent heart of stellar birth. Thanks for watching. If you enjoyed the video, please like, comment, and subscribe. Also, join our newsletter to stay informed with the latest discoveries shaping science and innovation. See you tomorrow with a new round of breakthroughs. Take care.